Hi, this is the first content video. Reminder that copies of the slides are available on the Blackboard site. Near the link where you found this video, there's a link with a corresponding name that has a PDF file containing the slides, and you're more than welcome to print out the copies of the slides before you watch the video and take notes as you go along. The first topic, called Euler Circuits, comes from sections 1.1 and 1.2 in our textbook. Let's look at a sample application. Suppose as some sort of fiendish punishment, somebody assigned you to paint the curbs in this subdivision. So there are cul-de-sacs and irregularly shaped streets. Your job is literally to walk along the edge of each curb and to paint parking spaces along them. This is typical of a situation in a branch of mathematics called management science or operations research. It's to find the best way to solve a particular problem, and what best is depends on the application that we're talking about. If you're talking about doing a job like painting curbs, you probably want to get done in the fastest way possible. If you're a company making a particular product like tires, maybe you want the cheapest way to manufacture a tire. Or perhaps you're an automobile manufacturer and you want to build up your reputation, and so for a given amount of money you want to produce the highest quality car. It's just human nature to try to get the most that we can out of the given resources, and that's what operations research is all about. Let's simplify the picture a lot. Instead of this huge subdivision, let's just look at a couple of city blocks like this and ask ourselves, what's relevant about this picture? Well, the tree, the car, the house, the sidewalk, none of that has any bearing on how we decide to go about painting the curbs. What's essential about curb painting is, of course, curbs. And so let's put a dot here at an intersection, and then let's put a curve, could be straight down along this to the next intersection, and put another dot there. And this curve that we just added stands for the physical curb that it went parallel to. Now here's another curb along here, and so let's draw another curve between these 2 points. And then here's a curb along here, so let's add a curve up to here, and you see on the other side is another curb, and we'd have to paint along that too, so it goes between the same 2 intersections, but we'll need another curve to represent this curb. And then if I finish off, I need to go along here and here and here and here. And now all of the information that I need to know about this picture is contained in the red curves and dots that I just drew. So we could replace this picture by this picture. Notice the similarity between this and this, but the advantage of the second picture is it only has the relevant information, so we won't be as confused about irrelevant parts of the problem. Now, I propose that we decide to start at vertex A, and by the way, the dots on a graph like this are called vertices, and the connections between the vertices are called edges. They can be drawn straight, as some of them here are, or curved. It doesn't matter. How are we going to start at vertex A and go around and paint every curb and end at vertex A? Well, if we start at vertex A, proposal that first we could go along from A to B, and then how about second we could go down to vertex E, and now you have a choice to make, and some choices are better than others. How about if we go back up this way and then over to C and then to F, E, D, and back to A. And that is a route going along the edges in the order we numbered them that goes across every edge, or in other words, paints every curb. There would be other possibilities as well, and perhaps you drew a different one that was just as good. So we are talking about graphs here. A graph is a finite set of vertices. They're labeled A, B, C, D, E, F here, and then G, H, I could also be part of it. And a finite set of edges. An edge has to join two vertices. In more complicated problems, we could actually also assign lengths to these edges. So maybe they represent physical things like the curbs in the previous problem, and we could have physical distances labeled on here. Or if there are streets in a city, perhaps we would put an indication that you could go from G to I, but not from I to G if this were a one-way street. So there are various ways that we can put additional information on a graph to add more realism to the problem. Here's an application, airline routing. So an airline wants to fly between these cities, and they decide, for example, that it makes sense to have a direct flight from Rome to Berlin, but maybe not a direct flight from Miami to Berlin, because perhaps that's too far for the aircraft to travel, or maybe there aren't enough people flying from between those two cities to justify a direct flight. And so possibilities for going from Miami to Berlin through London, for example. So airlines have very large problems. This problem only has 5 cities, but a real airline would probably have dozens of cities, and some of the cities would be connected by direct flights and others would not. We're talking about something called paths, which is a directed sequence of edges. In the picture that we drew before, we started going 1 and 2 and 3 and so on. What I've just drawn, just those 3 edges, is an example of a path. We're further interested though in a special kind of path called a circuit that starts and ends at the same vertex. So as it's drawn, I've started at A and ended at B. That's not a circuit yet. It is a path, but it's not a circuit yet. If I kept going as we did around back to vertex A, that would be both a path and a circuit. Now, what would determine the best route for curb painting? There are lots of different ways that we could go around through this graph and go across every edge. Here, for example, I could go 1, 2, 3, 4, and then back along this edge again, 5, 6, 7, 8, 9, 10, and come back to vertex A, and I've painted every curb. And here was another type of picture similar to the one, not quite the same, that we drew earlier. I think you'd all agree that this is a better way of doing it than this way, and the reason is it's shorter. You don't have to go across edges multiple times. That's called an Euler circuit. So both of these pictures show circuits. The one on the right shows an Euler circuit. That's a circuit that uses each edge exactly once. Not more, not less. The one on the left is not an Euler circuit because it used an edge more than once. Then the question becomes, which graphs have Euler circuits? For example, this one. Is it possible to, say, start at this vertex and go around using every edge exactly once and return to vertex A? Think about that for a moment. Well, let's just try. How about if I go here first, and then perhaps here? Is that the only thing that you could do? No. Most of these Problems have more than one solution, and some of them may not have a solution at all, and that's this question: does the graph have an Euler circuit at all? So then I could go here, 4, 5, 6, and then I have a choice, and maybe I could come up here, 7, 8, 9. Then how about we come back here and go 10, 11, 12, 13, and 14. Aha, there it is. That's an Euler circuit. This graph does have one. It has more than one. Here is one. This problem is named after Leonhard Euler, a mathematician that lived in the 1700s in a city called Königsberg, which was part of Prussia then, and I believe is now part of Poland. Königsberg was built on the junction of two rivers. So a river came in here, another river came in here, they joined, and they flowed out together out to the left. In this junction there was an island, and the city was built all around this surrounding junction, including the island. The townspeople had built bridges, 7 of them, shown in yellow on this picture. And people with too much time on their hands, there were a lot of rich people back then, just like now, and so they would sit around and think up math problems, I guess. And one of the questions they came up with is it possible to walk around Königsberg and cross over every bridge exactly one time? Every bridge exactly once, not more, not less. Well, what's important about this picture? The bridges, right? So how about I draw a curve across this bridge and call that an edge, and an edge has to join vertices, so I'll put those at the end of the edge. Now here's another bridge. Nothing in this problem said anything about walking across land. It's fine if you do that, it's fine if you don't. And so I claim that this point on the land, and this point on the land, and this point on the land, all of those on the island, can be thought of as the same point. It really doesn't matter where you are on the island, just that you've crossed a bridge to get there. So the point being, I'm going to draw another edge through this bridge, and we'll have to walk across that edge or that bridge as well. But then let's, for simplicity, join it here. This is just one edge. And then over here is another bridge, and it'll need an edge. Now, I'll put a vertex here because this point, for purposes of this problem, is definitely different than this point. To get from here to here, you have to cross a bridge, whereas to get from here to here, there's no reason why you do. So, in other words, this needs a new vertex. This is a different point than this point. And then we could draw an edge between these 2 points. But you see up here, to get from here to here, I could walk across land, and so nobody cares if I do or don't do that. And so I think that we should take this edge and join it in at this vertex. And then to finish the picture, go across here, and that's still a different area of land. So let's draw a point there. And this bridge joins exactly the same 2 bodies of land as this one did. So let's draw an edge that goes here, and an edge that uses or goes across this bridge. And then that seems to be it. We've made a graph. It has 7 edges because there were 7 bridges to begin with, and it has 1, 2, 3, 4 vertices. Then the question that the townspeople of Königsberg had is the same question as, does this graph have an Euler circuit? To go across a bridge is to go along an edge, the corresponding edge. This is just a bigger picture of the slide. And you might experiment on this empty slide and see if you could go across each bridge exactly once. Let's go on to the two questions now that we really want to find an answer for in general, not just for a particular graph, but in general. How can you determine if a graph has an Euler circuit? And if it does have an Euler circuit, how can you find one? So here's a very simple graph. 1, 2, 3 vertices and 3 edges. Does this graph have an Euler circuit? Well, if I start at this vertex, the only choice I have is to go along this edge, and then maybe along this edge, and now if I'm trying to complete a circuit, I have to come back and reuse the edge that I already did, and then it won't be an Euler circuit. It'll be a circuit, but not an Euler circuit. So I don't think this particular graph has an Euler circuit. We've seen some graphs that do, now a graph that doesn't. To answer the question about which graphs have Euler circuits, let's look at two concepts, one called connectedness. A graph we'll say is connected if a path goes between any two vertices that I pick. So in this picture at the bottom, for example, there is no path from B to C. There's no path from A to C or D to C for that matter. But as soon as I find a pair of vertices like B and C where you just can't get there you can't get to C from B, then that graph is not connected. Another concept is the so-called valence of a vertex. Valence is a word that comes from chemistry, and for our purposes it'll mean the number of edges that meet there. So each vertex has a number in parentheses near it, and for example, the valence of vertex D is 3 because there are 1, 2, 3 edges coming into it. The valence of vertex B is 2, and the valence of vertex C is 0 because no edges come into it. And these two concepts, connectedness and valence, turn out to be exactly the ideas that we'll need to answer the question about which graphs have Euler circuits. A graph will have an Euler circuit if it satisfies both conditions. Let me give them, and I hope they'll seem very reasonable. First of all, we talked about connectedness. What does connectedness have to do with an Euler circuit? Well, if a graph isn't connected, you simply can't get from one. There are a pair of vertices where you can't get from one to the other, and so you can't possibly hope to construct an Euler circuit for a graph that isn't connected. And so that'll be one of our conditions. The other condition has to do with valence. Let's flip back and look at a graph like this one, for example. It's connected, but we said it didn't have an Euler circuit. What about the valences? Here's a valence 2 vertex, a valence 3 vertex, a valence 1 vertex. Now, there's a problem at a vertex like this. I'm going to use the one edge to leave the vertex, and then I can't get back except by going along the edge that I've already used. There's also a problem at a vertex like this. It has 3 edges coming into it. I'll leave on one edge, I'll come back on the other, I'll leave on the third, and then I could never finish my circuit by coming back here. So the issue is whether the edges come in pairs or not. At a given vertex, I would like for the edges to come in pairs, or in other words, that the valence of every vertex is even. Why? So that I can come in on one of the edges to that vertex and then leave on another. And if the valence is, for example, 4, I'll come in on the third edge and I'll leave on the fourth edge. But if I have a valence like 7, then I don't have pairs to arrive and leave upon. And that graph would not have an Euler circuit. So to summarize, the graphs that have Euler circuits are exactly those that are both connected and have every vertex with even valence. Now, let's talk about the other question that we had. Suppose a graph does have an Euler circuit, I know that. How can I find one? I'd like to find an algorithm for finding an Euler circuit. An algorithm is a sequence of explicit steps. This is like when you write a computer program. You have to tell the computer exactly what to do, and then what to do next, and then what to do next, and then what to do next. Computers don't have creativity. We do that in real life too if we're giving directions. So to go from Marion to Los Angeles, I take Indiana 37 to I-465 to I-70 and so on, and I keep giving these roads to take next, and I should do it in the order of travel. We found Euler circuits for several graphs before, and they were pretty easy to do by hand. And so why is it important to find an algorithm, or why is it important to be able to write a computer program to do this kind of thing? Two reasons. One is that most graphs that we want to do this with are large. For example, if you're talking about routing airplanes between various cities, perhaps the graph may have 50 or 80 or 100 vertices and dozens and dozens and dozens of edges. And the problem is starting to get too large for us as humans to be able to, first of all, draw the graph, and then second of all, to be able to wade through the hundreds or even thousands of edges that are needed. Computers are good at that, but we have to tell them exactly how to do it. The second point is related to that. Computers don't have intuition, so the computer is not going to be able to say, oh, I can figure this out. No, you have to tell it step by step by step. So we really do need an algorithm for this type of situation. To describe the algorithm, let's first state what an edge called a bridge is. A bridge is an edge which, if you delete it, it would increase the number of components of the graph. So let's talk about what that means with this example at the bottom. Here's a graph with 7 vertices, A through G, and the graph is obviously not connected. You can't get from G to C, for example. So right now the number of disconnected components of this graph is 2. Here's 1, and here is the second. And now I say, what would happen if, for example, I deleted the edge between A and B? Now how many components are there if that edge AB is gone? Well, A, F, G, and B are still all connected to each other, so that's one connected component. And over here, I haven't touched this, this is still another component. So there are still 2 components to the graph, and therefore AB must not have been an edge, because deleting it didn't increase the number of components. But suppose instead of that edge, I delete this edge. Now, how many components are there? 1 here involving this block, 1 here. Vertices D and E and the edge joining them are another component. And now with this edge gone, vertex C is a third component. You can't get from vertex C to either of the other 2 components, so it's a third component. And deleting edge CD did increase the number of components of the graph. So CD is an edge. What is a bridge? What other edges in this graph are bridges? Well, if I deleted DE, the same thing would happen. So it's a bridge, and none of these others by themselves, just deleting any one of these, would not increase the number of components. So the bridges of this graph are CD and DE. Using that language then, here's the algorithm for finding an Euler circuit. Start at any vertex. Any vertex. If this graph does have an Euler circuit, then it doesn't matter which vertex you start at, you'll still be able to find an Euler circuit starting from that vertex. And then here's the heart of the algorithm. From your starting vertex, choose an edge. If you have a choice, you can make any of those choices except if one of the choices is a bridge and one is not. If so, then don't use the bridge. Only use the bridge as a last resort. If there's another edge to choose that's not a bridge, choose it first. Move along the edge that you've chosen to the next vertex. Delete the edge that you just traveled on, and then go back and repeat steps 2, 3, 2, 3, 2, 3, 2, 3 until all of the edges are used. Let's show an example. Does this graph have an Euler circuit? Well, it's connected, and I look around and go through and examine the valences of each of the vertices, and I see things like 4s and 2s, and I guess that's all. So those are both even numbers, and so this graph does have an Euler circuit. Then let's just say we want to start at vertex A. Are any of the edges of the graph bridges? No. So from vertex A, I can pick any edge that I want to go along, and suppose I pick edge number 1 and go to vertex B. Now the algorithm says once you've gone along an edge, delete it. And so that edge is gone, and now I'm at vertex B. And I have 3 choices of edges going out of vertex B. Are any of them bridges? No. So just pick one. I'll pick this vertex, this edge labeled 2, and go over to vertex C, and then delete the edge that I just used. Now I'm here at vertex C. Again, I have 3 choices. None of those 3 edges are bridges, so I can just pick one. I'll pick to go along edge 3 to vertex D and delete it. And now I have 3 choices of edges leaving vertex D. Here the decision comes into play. Can you see that edge DE is now a bridge once the 3 edges that I've used are deleted? DE is now a bridge, and so going along this edge would not be a smart thing to do. Once that edge is deleted, I'd never be able to get back over and use the edges over here. So the algorithm says, okay, choose something else. Don't choose edge DE, but choose either of the other edges. And so here I could go 4 and 5 and so on. I won't finish the picture, but you can see that you can walk yourself along. Then you use the bridge, but now you're over here where you need to be, and you can finish off and end up at vertex A. And here is an example of a numbering that does that. A little different one than I started to choose in the previous slide. And that completes this lesson over Euler circuits.